Now that we've reviewed the equations for conic sections, and we've looked at how we can take the rectangular equations for a curve and change them into parametric equations, we're going to take it one step further and use calculus to find the first derivative of a set of parametric equations and then the second derivative as well. To do this, we need to know this. If x is equal to f of t and y is equal to g of t, then the slope of the curve C at point x, y is equal to dy dx, just like it is for rectangular equations. But we can break this down into dy dt over dx dt. And this is, of course, assuming that dx dt does not equal 0. Okay, so this is what we're going to do. We don't have to change over into the rectangular equations to differentiate. We can differentiate this way. So here's our parametric equations. X is equal to sine of t, y is equal to cosine of t, and we want to find dy dx. Well, just from our definition, we know that this is dy dt over dx dt. So let's see if we can work from there. For y, we've got dy dt is equal to, the derivative of cosine is negative sine of t. And then for dx dt, the derivative would be cosine t. So I'm going to put these two here. So I've got negative sine of t over cosine of t. So negative tangent of t. Okay. If I wanted to, I could find higher order derivatives by just repeating this process. And we'll do that in just a minute. So here's a new set of parametric equations. And this time we have a limitation on t that it has to be greater than or equal to 0, which just makes sense with that square root of t, that we want to limit t to positive numbers or 0. The other thing that we're going to add now is we're going to look at 2, 3. This point is where we want to find our slope, and then we're going to take the second derivative and find the concavity at that point. So dy dt is equal to 1/2 of t dx dt is equal to 1/2 of t to the negative 1/2. Okay, so when I put this together, I've got dy dx is equal to 1/2 t over 1/2 t to the 1/2. I'm sorry, to the negative 1/2. Which gives us, these cancel out, I've got t to the 3/2 power for my dy dx. Okay, now let's look at the second derivative. And we write that like this. Should be dy dx. Over dx dt. Okay, and then we're going to substitute in here and have d dt of t to the 3/2 over dx dt. So the derivative of this is 3/2 t to the 1/2 power. And this one we already figured out earlier is 1/2 t to the negative 1/2 power. Okay, and all that simplifies to 3t. So my second derivative is 3t. Let's put that over here. Okay, now we're going to look at our point for xy equals 2, 3. Okay, it follows that t is 4. So we're going to look at that point where t is 4. So 3 times t. So the slope would be, let's make this 4 to the 3/2. So square root of 2 cubed would be 8. And then this is our second derivative. So the concavity, I'd have 3 times 4 would be 12. And we know that 12 is greater than 0. So the concavity would be up. So for this set of equations, at the point 2, 3, we have a slope of 8 and a positive concavity, so it's concave up. Okay, the next curve we're going to look at is called a prolate cycloid. And it looks something like this. And the interesting thing is, at this point, I have 2 tangent lines. One going that way, one going that way. And so at this point, I've got two different slopes. Okay, the equation for this shape is x equals 2t minus pi sine of t, and y equals 2 minus pi cosine t. Okay, and this point of intersection for this particular set is 0, 2. So that's the point where we're going to find our first, and we'll just find the first derivative for this one. Okay, so when t equals positive or negative pi over 2, x equals 0, and y is equal to 1. I'm sorry, y is equal to 2 because we multiplied by 2. Okay, so now let's find dy dx. Y dt over dx dt. So this is going to be pi sine t. And here I've got 2 minus pi cosine t. So we get that dy dx is negative pi over 2 when t equals negative pi over 2. And dy dx is equal to positive pi over 2 when t equals pi over 2. So let's look at our two tangent lines. These are our two slopes, negative pi over 2, positive pi over 2. We know that they intersect at this point, so the y-intercept is 2. So I'm going to have y minus 2 is equal to negative pi over 2 x. And y minus 2 also equal to positive pi over 2 x. So I've got two tangent lines. The equations are the same except for the sign of the slope. In our last example, we looked at a curve called a prolate cycloid. In this example, we're going to look at another curve called an epicycloid. Okay, let's just look at different kinds of cycloids first. If I have a wheel that's running down a straight road, and there's some reflector or light or something like that on the wheel, as it goes down the road, we see that light make a pattern like this. And this is called a cycloid. Now if I take this picture and I curve it around and use a large circle being circumscribed by a smaller circle, then I get this shape, which is called an epicycloid. And all these cycloids have in common, technically they are not continuous functions because they have these points in them. but we can work with them by saying that they are piecewise smooth curves, which means that most of the time they're smooth, but they do have these little breaks in them, and so they're only piecewise smooth. In our next example, we're going to look at this epicycloid, and the center circle has a radius of 4, and then the smaller circles each have a radius of 1. And it really is just one circle as it's rotating around the outside of the larger circle. And the parametric equations for this epicycloid are x equals 5 cosine t minus cosine of 5t, and y equals 5 sine t minus sine of 5t. So those are our two equations for this outside curve. Okay, and we want to use calculus with our parametric equations to find the arc length of this epicycloid. When we're working with shapes like this, it's very important to pay attention to your limits of integration. Okay, if I don't limit my integration properly, I might be doing more than one rotation. And so, of course, my arc length will be too large. But let's take a look at this. I'm actually going to find just one of these pieces and multiply it by 4 because they're all the same. So my arc length is equal to 4 times the integral. We're going to go from 0 to pi over 2. And we'll take that first derivative and square it, plus dy dt. Same thing here, square it, dt. Okay, and this is the parametric form for the arc length integral. Okay. So let's take these derivatives. We get negative 5 sine t plus 5 sine 5t plus 5 cosine t plus minus 5 cosine 5t. And we're going to square that and take the square root of all of it, dt. Okay, now I've got factors of 5 out here, and they're all squared. And then we take the square root, so I'm going to take out a factor of 5 and put it out front with the 4, so that gives me 20. And still inside the square root, I've got 2 minus 2 sine t sine 5t minus 2 cosine t cosine 5t dt. Now I'm going to use the difference formula for cosine to clean this up quite a bit. And I'm going to have 20 times the integral from 0 to pi over 2 square root of 2 minus 2 cosine 4t dt. And then I'll use a double angle formula. Which gives me 4 sine squared 2t dt. Okay, and then when I take the square root of that, that's going to give me another factor of 2 out here, so I'll have 40 sine of 2t dt. Okay, now I'm ready to actually integrate. And I get negative 20 as the cosine of 2t from 0 to pi over 2, which gives me a final answer of 40. So the length of this arc all the way around is 40. And if you want to do a kind of a reality check on that, let's look at the circumference of the circle. This circle has a radius of 4, so the circumference is 2 pi times 4, so this would be 8 pi, which is approximately equal to 25, rough estimate, and this is 40. So if this circle is 25, does it make sense that this part, which is going in and out, would be 40? It seems like a reasonable answer. In the same section where we originally studied arc length, we also looked at finding the surface area when we revolved an arc around an axis. So we're going to modify this again to do the same thing with parametric equations. Okay, so our formula for surface area, 2 pi integral from a to b g of t as the square root of dx squared dt plus dy dt squared dt. Okay, and this is if we want to rotate about the x-axis. If we wanted to rotate about the y-axis, we would use f of t, and the rest of it is the same. So this is for the y-axis. Okay, sometimes to make this simpler, we say that ds is equal to this big square root dx dt squared plus dy dt squared, and then take the square root. And that kind of simplifies and reduces the amount of writing we need to do. Okay, so in this picture, we've got an arc really from just 3, 0 up to 3 over 2 and 3 square root of 3 over 2. This is part of a circle with radius 3, and it goes from just here to here, so not even a quarter of a circle. And we're going to rotate it around the x-axis. So rectangular equation of the circle is x squared plus y squared equals 9. But we want to go from 3, 0, which is this point on the x-axis, to 3 over 2, 3 root 3 over 2. And we want to find the surface of this kind of shallow bowl shape that we make by doing that. Okay, I can represent this curve with these parametric equations. X is equal to 3 cosine t, and y is equal to 3 sine t. And we're going to say that t is in between 0 and pi over 3, because that's what would get us to this point. Okay, let's write out our equation now. S is equal to 2 pi times the integral 0 pi over 3 sine t. So that was our g of t, times the square root of negative 3 sine t squared plus 3 cosine t also squared dt. Okay, so now I'm going to take this factor of 3 out, so I have 6 pi and just have sine t now. And in here, I'm going to take out the 9 after I square both of these and just put it out front inside the radical. Okay, we know that sine squared plus cosine squared equals 1. So all that's really left inside here is this 9, and square root of 9 is 3. So now I have 6 pi times the integral of 3 sine t dt. And I can bring the 3 out, and when I integrate, I'm going to get a negative, so it's going to be negative 18 pi of cosine t evaluated from 0 to pi over 3, which is equal to negative 18 pi times 1/2 minus 1. So this is negative 1/2 times the negative 18 is going to give me 9 pi for my area.